All right, welcome to the Explainer. Today, we're diving deep into the secret science of plastics, what gives them their amazing and sometimes, let's be honest, kind of frustrating powers.
Let's kick things off with a little puzzle. When you've probably got sitting in your kitchen right now, think about a plastic water bottle and, say, the handle on a cooking pot. They both feel like plastic, right? But here's the weird part. If you heat them up, that bottle will melt into a gooey puddle that you could reshape. The pot handle? It just burns. It chars and smells awful. So what's the deal? Why the huge difference?
To figure this out, we need to go on a little journey. We've got to shrink ourselves down, way down, to the molecular level. Because the answer isn't in what we can see with our own eyes. It's all hidden in the invisible architecture that holds these things together. Okay, so to really get this, we're going to have to think like molecular architects. Let's start at the beginning, with the basic recipe for how you even make a plastic in the first place. Everything, and I mean everything in the world of plastics starts with this little guy, a monomer. Just think of it like a single Lego brick, or maybe one link in a chain. It's the smallest, most basic building block you've got. So what happens next? Well, through a chemical reaction called polymerization, you start linking these monomers together. And we're not talking a few, we're talking thousands, sometimes even millions of them. When you do that, you get a polymer. Poly just means many, and mer means part. So many parts. It's that simple. You've just created a giant molecule, a macromolecule. Let's look at a real-world example. You start with these simple little molecules called ethylene monomers, link them up in a long chain, and boom, you get polyethylene. You've definitely heard of this one, even if you don't know the name. It's the plastic in your shopping bags, your milk jugs, your water bottles. It's literally one of the most common plastics on the planet. And here's a key takeaway. With polymers, size really does matter. The longer you make these chains, the higher their molecular weight, the tougher and stronger the final plastic becomes. It's a direct relationship. Okay, but it's not just about how long the chains are. That's only part of the story. The real magic, the thing that gives us this incredible diversity of plastics, is how those chains are arranged. Seriously, in the world of polymers, arrangement is everything. So it turns out there are four basic ways, four fundamental blueprints for organizing these long molecules. And you gotta pay attention here, because each one creates a material with totally different powers. First up, you can have linear chains. The best way to picture this is like a neat bundle of uncooked spaghetti. The chains are all lying side by side, pretty orderly. And because they're just lying next to each other, they can kind of slide around, which is what gives these plastics their flexibility. Okay, option 2. Branched chains. Now, instead of neat spaghetti, imagine a huge tangled pile of tree branches. All those little side branches get in the way, right? They snag on each other, and it makes it way harder for the chains to move around. And that makes the plastic tougher. And then things get really interesting. We can do something called cross-linking. This is where you create strong, permanent chemical bridges. They're called covalent bonds that literally tie the chains together. They're not just tangled anymore, they are physically locked to each other. They're not going anywhere. Take that idea to the extreme with a ton of cross-linking, and you get our final structure, a network. At this point, you don't even have individual chains anymore. The whole thing has become one single, giant, three-dimensional molecule. And as you can imagine, it is incredibly rigid and super strong. So you see? The big takeaway here is that the structure, whether it's neat and tidy or all tangled up like a bowl of spaghetti, is what directly gives a plastic its personality. It's the difference between a flimsy plastic bag and a super tough construction helmet. And these different molecular blueprints, well, they lead us straight to the two major families of plastics. And guess what? This is exactly what we need to solve that puzzle we started with. Okay, check this out. This chart lays out the Great Divide perfectly. On one side, we've got thermoplastics. Remember those linear or branched chains? That's them. The chains are just hanging out next to each other. So when you add heat, they can start to slide around, and the whole thing softens and melts. And that's key, because it can melt, you can recycle it. Now look at the other side. Thermosets. These are our cross-linked or network plastics. Those chains are locked together permanently. So what happens when you heat them? They can't melt. The heat just destroys the structure, and they char and burn. No remelting, no recycling. Right, so now we have all the clues. Let's go back and finally solve our kitchen mystery. It's simple now, right? Your plastic bottle is a thermoplastic. It's made of those long, linear chains. Add heat, the chains get energized, they start sliding past each other. And poof, it melts.
The pot handle? That's a thermoset. Its molecules are locked into that super strong cross-linked network. Heat can't make those chains slide. It can only break them, which is why it just burns.
So you might be wondering, what about something like rubber? That's kind of in between, right? Well, that belongs to a cool category called elastomers. Think of them as being just a little bit cross-linked. There are just enough links to hold the chains together, so when you stretch it, they snap right back into place, but not so much that it becomes rigid. This structure is amazing at absorbing energy, which is exactly why we use them for things like car tires and shock absorbers.
Okay, so this isn't just a cool science lesson. Understanding this stuff at the molecular level has massive real-world implications, especially for how we use and, maybe more importantly, reuse these materials every single day. So how does this connect to that little triangle with a number in it you see on the bottom of plastic containers? Well, now you know. Recycling, the whole process of melting stuff down and reforming it, only works for thermoplastics. Since their molecular chains aren't locked together, we can melt them down and give them a new life. Those little numbers, they're just codes to help us sort all the different kinds of thermoplastics so they can be processed correctly.
But what's next? You know, the big conversation right now is all about the future of plastics, and a huge part of that is biodegradable plastics. Scientists and researchers are working on creating totally new polymers, not from petroleum, but from renewable stuff, like starch from potatoes and corn, or even from fermented sugar. And the whole point is to design them so that microbes in the environment can actually break them down. And that's where we'll leave it, with a big question for the future. As we get better and better at engineering these new polymers, building them from plants instead of oil, what new incredible properties will we discover? How will our ability to be molecular architects, designing materials from the ground up, totally change the stuff that builds our world? It's pretty exciting to think about.